Hello, my name is Peyton Correa, and I am a member of the PCI Big Beam team from Northern Arizona University, along with Isabella Velasco, Caitlin Yazzie, and Zachary Fukumoto. The PCI Big Beam competition involves student teams designing and testing an 18-foot pre-stressed and precast concrete beam. But first, let's get a more concrete understanding of pre-stressing. Pre-stressing concrete is a process of adding internal stresses to a part of a structure. It is done by taking long metal pre-stressing strands in an empty concrete form and applying tension to them. Tension is applied, the concrete is poured, allowed to cure, then the strands are cut, releasing the strand's tension forces. This causes the beam to camber up due to the compression induced into the beam. Pre-stressing is a very cost-effective process because the internal compressive forces can counteract the loading, which limits cracking. This means that the steel reinforcement is less exposed to the elements, so experiences less corrosion, creating a more durable structure. This test setup reflects the competition rules with a point load at midspan and another point load 3 feet off center. The teams are graded on how close we are to the lightest beam, the lowest cost, the most accurate predictions, and the highest deflection at 32 kips. We also had to make sure our beam cracked between 20 kips and 32 kips of total applied load, and fail between 32 and 40 kips. But don't worry, I'm not deflecting on showing you what our design is. We started our calculations by first defining our variables. We had complete freedom during this process and could change our dimensions, steel types, steel sizes, locations, and choose a lightweight or normal light concrete mix. Our losses were calculated, and then we used the adjusted stresses and forces with the strain compatibility method to find our nominal forces. We also considered the development and transfer lengths. We calculated our stresses at transfer and tests to ensure code compliance and account for the concrete strength improving as it continues to cure. We made sure our stresses were within the allowable limits. Our calculations were set up to calculate the applied forces at a point during the test. This allowed us to iterate and determine where our moment capacity equaled the max applied moment. Then, we calculated the shear capacity and demand and tested different stirrup spacings so that our capacity would exceed the shear forces our beam experiences. Our deflection was initially calculated using standard equations in the superposition method. Then we used the method of virtual work, data from the program response, and an Excel file of calculations to refine our deflection. Here's our final cross-section design. We have two pre-stressing strands in the top and bottom flange, with the top flange strands only tensioned enough to hold the stirrups in place. Our pre-stressing strands are spaced 4 inches apart, and we opted to not fillet or chamfer our corners in order to make our design more constructible. We tested different stirrup spacings, but settled on 7-inch and 11-inch spacings to save on costs and weight where it was not needed. The red line in the graph shows the shear demand, and the dashed lines show that our spacing exceeds the demand. Due to the different spacings, in our shop drawings, we specified that the side with the 7-inch spacings would have an extra lifting loop so that we can make sure it was tested properly and oriented in the lab correctly. After finishing our design, we coordinated with TPAC, our PCI producing member, in order to fabricate our beam and ensure that we both understood each other's design interpretations and that our design was constructible. Caitlin, Isabella, and I were able to visit TPAC for fabrication. We compared our planned set design to the empty concrete form. We also had the fantastic opportunity to discuss pre-stressed precast concrete with TPAC employees. We also ensured that the form, strand placement, and stirrup placement were as we designed. TPAC also conducted a spread test to ensure our concrete was mixed properly. As shown in the table, our mix design had slightly more air content, which contributed to a lighter unit weight. TPAC shipped our beam the 2-hour journey to NAU Labs in Flagstaff, Arizona, where we tested cylinders made from our batch of concrete to gauge when our concrete was close to our design strength, and also to get a more accurate concrete strength value to finalize our predictions. Then it was time for our test. We created a load deflection graph in order to determine mathematically the time that our beam cracks. Cracking is shown in the graph when it starts to become non-linear, or when it curves right about now. Now our cracks are all pointing to where our beam will eventually fail. Let's see that again, and we can see that the top of the beam also starts to crumble. And one more time, just for fun. We were very excited to see how our beam performed and the very low differences. This was a learning process, and we really enjoyed the opportunity to learn about pre-stress design. In the future, we will definitely use a higher sample size of concrete test cylinders to predict the concrete failure point and ensure we have high-quality cylinder bricks as well. Our team learned a lot about the engineering design process, technical design, and code requirements, and we are really excited to put these into practice throughout our careers. Thank you to everybody who helped make this beam possible and helped us with our design, our fabrication, and gave us feedback throughout the process. Thank you all, and good luck to the other competitors.